Have you ever wondered why massive, multi-million-dollar tech projects frequently just collapse into utter chaos? I mean, why do major apps crash on launch day, or software updates break the very systems they were literally supposed to fix? Well, imagine trying to construct a 100-story skyscraper by just handing a bunch of workers some steel and concrete and saying, hey, figure it out as you go. It would be a total disaster, right?
But look, that is exactly what happens in the tech world, when teams just skip the planning stage. The answer to our question lies in ignoring the blueprint. Jumping straight into writing code without a solid plan is the exact equivalent of building that skyscraper without any architectural drawings. It might look okay on the first floor, sure, but by floor 10, the whole thing's coming down. So, welcome to this explainer. Today, we're going to decode the software development lifecycle, or SDLC, using a metaphor that just makes perfect sense: the construction site. We're going to demystify how abstract lines of code are transformed into towering digital structures that run our modern world, and really, why respecting this process is the only way to build something that actually lasts.
Here's our roadmap for today. First, we'll gather the blueprint. Second, we'll design the architecture. Third, we'll write and test the code. Fourth, we manage the chaos. And finally, we'll estimate cost and effort.
All right, let's jump right into Section 1, Gathering the Blueprint, the real foundation of software.
Before you pour a single drop of digital concrete, you absolutely must know what the building is actually supposed to do. I mean, is it a hospital, a residential tower, a shopping mall? We answer those questions through something called requirements engineering. Basically, this is the process of determining exactly what services a customer actually needs and the limitations that are going to affect the build. Take the Medicare system, or the MHCPMS mentioned in our sources, for example. Before developers wrote any code at all, they had to sit down with the real stakeholders, doctors, clinic staff, IT managers, just to discover precisely what features they needed to do their jobs effectively.
Now, those needs essentially break down into two distinct categories. First up, we've got functional requirements. This is literally what the system does, the services it has to offer. So for a clinic, a functional requirement is that users must be able to search appointment lists. Easy enough, right? On the flip side, we have non-functional requirements. This is all about how well it performs. It covers the heavy constraints like security, reliability, and response time. Think about it. A system might perfectly search an appointment list, but if it takes 10 minutes to load, or if patient data isn't secure, the entire system completely fails.
Okay, moving right along to Section 2, Designing the Architecture, or Drawing the Framework.
So transitioning from written text documents to actual structural design, we now need to lay out the skeleton and the plumbing of our software skyscraper. One traditional, tried-and-true way to draw this framework is through structured analysis. This is a top-down methodology that takes incredibly complex systems and just breaks them into manageable, bite-sized processes. Analysts use tools like data flow diagrams, or DFDs, to literally model how information moves. For example, think of your standard online shopping cart. A DFD maps out exactly how a customer's input flows into an order check, then moves to credit validation, and finally outputs as a confirmed purchase. It basically visualizes the entire assembly line of data.
But, structured analysis isn't the only way to design things. While that approach is process-focused and top-down, modern object-oriented analysis, or OOA, is bottoms-up. It models a system based on, objects that contain both data and behavior. Take an ATM machine, for instance. An ATM class diagram would map out the physical ATM, the bank database, and the customer as separate objects that interact with each other, using cool principles like encapsulation to hide all their internal workings. It's a highly reusable and super scalable way to build modern software.
Let's dive into Section 3, Writing and Testing Code. This is where construction and inspection happen.
With the architectural blueprints finally signed off, it is time for our coders to pour that digital concrete. And just like in real construction, the choice of material really matters. Developers are looking for readability and brevity to keep things clean, alongside portability so the code can run anywhere. You're also going to need strong error checking, high execution efficiency, and modularity so it can be built in blocks. Finally, it needs to be widely available and cost-effective. Hit all these marks, and I promise you, your build process will be incredibly smooth.
But let's be real, code is never perfect on the very first try. Just doesn't happen. That is exactly why we rely on black box testing. This is an inspection method where the tester examines the functionality of the software without ever peering into its internal structure or code. You really don't need to be a programmer to do this. You're simply acting as the end user, putting inputs into a black box, and just verifying if the correct output pops out on the other side.
The difference between testing types is honestly night and day.
Black box testing is all about that external user experience, like does clicking submit actually submit the form? Conversely, white box testing, which is sometimes called glass box testing, requires deep programming knowledge. This is where the inspectors look directly into the internal coding. They're checking the hidden infrastructure, the loops, and the data flows to ensure the internal plumbing isn't leaking anywhere.
So, how is a black box test actually organized? Well, you start by reviewing the original blueprints. From there, you choose valid inputs to ensure it works, but you also throw in invalid inputs just to test its absolute limits. You bundle all these into specific test cases, run them, and then compare the actual output against your expectations. Finally, you send it all back to the developers to fix the bugs. It's a rigorous, constant cycle of quality control.
All right, on to Section 4, managing the chaos through oversight and maintenance.
Imagine you have hundreds of workers building a massive digital skyscraper, and suddenly the client says, actually, I want a helipad instead of a penthouse. That causes absolute chaos, right? You can't just let a rogue developer rip up the code. Instead, you have to use a strict change control process within configuration management. It goes like this. First, identification of the change request. Then validation to ensure it's a legitimate ask. Next is analysis to see how badly it impacts the budget and timeline. Step 4 is control, where top authorities actually approve or reject it. If it is approved, we move to execution. And finally, we close the request once it's fully integrated and tested. This strict process is literally what prevents a single random change from collapsing the entire project.
Which brings us to our final phase, Section 5, estimating cost and effort. Let's talk about the budget.
Because let's face it, none of this matters if the project runs out of money halfway through. To mathematically estimate the sheer amount of resources required to make this digital building a reality, project managers rely on some pretty powerful formulas. One of the absolute most famous is the COCOMO model, introduced by Dr. Barry Boehm. COCOMO stands for Constructive Cost Model. It basically calculates effort, time, and cost based on the complexity of the project. And it comes in 3 flavors: basic, for quick, rough estimates early on; intermediate, which adds cost drivers like team experience into the mix; and detailed, which is reserved for massive, highly complex projects that require serious risk assessment.
Now, another brilliant method is the function point technique. This sizes software based on its actual utility, rather than just guessing by counting lines of code. You evaluate parameters like external inputs coming in, external outputs going out, external inquiries, and the complexity of the internal and external logic files storing all that data. By assigning weights to all of these components based on their complexity, managers can mathematically determine the true size and scope of the software. And when you run all that complex algebra together, factoring in total function points, the monthly budget, the team's productivity, you get a really punchy bottom-line resolution. In one of the exact project scenarios from our source data, calculating the cost of each specific functionality yielded a precise cost of $618.50 per function. Having that kind of concrete, hard number allows a project manager to plan their budget with absolute laser precision rather than just guessing in the dark. And that brings us to the end of our explainer. We have gone all the way from gathering the initial blueprint to calculating the final cost per function. So, I want to leave you with this final provocative thought. If building software is exactly like constructing a massive skyscraper, in your next project, are you taking the time to lay a solid foundation? Or are you just pouring code into the dirt and hoping it stands up? Respect the blueprint, respect the life cycle, and your digital structures will absolutely stand the test of time. Thanks so much for joining me, and keep learning.